In this video, we're going to be talking about vectors in 2 dimensions. Some quantities, such as length, area, and temperature, are determined by a number which is called the magnitude. Such quantities are called scalar. On the other hand, to describe the displacement of an object, 2 numbers are required, the magnitude and its direction. Similarly, while describing the velocity of a moving object, we discuss the speed and direction of travel. Quantities such as displacement, velocity, acceleration, and force that involve magnitudes, as well as direction, are called direct quantities. One way to represent direct quantities mathematically is through the use of something called a vector. Let's define what a vector is. A vector in the plane is a line segment that has magnitude and length with an assigned direction. The vector AB, as shown, has initial point A and end point B. Its magnitude is denoted by these 2 vertical bars that look like absolute value signs, and then AB with an arrow over it. So here in this picture, let's just highlight this has initial point A and end point B, and that is the vector AB. Similarly, if I have an initial point of C and an endpoint of D, then we call this vector CD. And we could really do this with anything. Let's say this point is O and this point is P, then we would call this vector OP, and we would just put a little arrow above it. 2 vectors are considered equal if their magnitude and direction are the same. All of the vectors that we just showed up above in this box are the same vector, even though they have different names. Let's talk about adding vectors together. To find the sum of 2 vectors geometrically, we have the following options. Our first option is have one of the vector's initial points start at the terminal point of the other vector. The resulting sum vector shares its initial point with the first vector and shares its terminal point or end point with the second vector. So that means that my resulting sum vector, if I wanted to add these 2 vectors u and v together, would start here and it would end here. And so I'm going to connect those with a line. All right, so I went ahead and I connected them with a line segment, and then also notice that I placed this arrow here because, again, vectors must have a direction. So if I were to label this vector, this is the vector u plus vector v. So that is our new resulting sum vector. The second way we could do this is we could draw the 2 vectors so that they have the same initial point, and then we can create a parallelogram, and its diagonal is the sum vector. So I'm going to go ahead and fill in the parallelogram, and then we can go from there. Okay, so now my sum vector is going to start here and end here because it's going to be the diagonal of our parallelogram. So let me go ahead and connect those, and then that will give us our sum vector. All right, so here is our new vector, vector u plus vector v, and that's our sum vector there. So those are 2 ways that we could draw the sum vector when we're given 2 vectors. Example 1 says sketch the sum vector, vector u plus vector v. I like the first option, so I'm going to go with that one instead of using the parallelogram method of drawing our sum vector. So what I like to do is I would draw u, so this is vector u, and then vector v, I'm going to start its initial point at the end point or terminal point of vector u, and I'm going to draw that, and it's going to look something like that. That's going to be vector v, and then the resulting sum vector would start here and end here. So I'm going to go ahead and connect those. And then the arrow is going in that direction. And so we have vector u plus vector v looks like that. And there is our answer. I went ahead and put in a more computerized drawing just so that you can see better, since the earlier answer I drew by hand. So the orange vector that we have here is our resulting sum vector. Let's talk about multiplying a vector by a scalar. For some real number a and a vector v, we have that the vector a times vector v is a new vector and it has magnitude. This first set of vertical bars are absolute value bars, and then the second notation is the magnitude of the vector v. They don't quite work exactly the same because one is a number and one is a vector. So just know that these here for A are absolute value bars. And we'll talk about later in the video how we take the magnitude or find the magnitude of a vector. The direction of the vector AV depends on the value of A. So let's go through the different scenarios. If A is positive, then the new vector has the same direction as vector V. If A is negative, then the new vector has the opposite direction as vector V. If A is equal to 0, then the new vector is equal to the 0 vector, which represents no displacement. And then if the absolute value of A is greater than 1, that means the vector stretches. If the absolute value of our scalar A is between 0 and 1, that means that the vector shrinks. Let's go through an example. Example 2 says vector u is given, draw the requested vectors. So here we have a picture of our vector u, and part A we want to draw 1/2 times the vector u. So what we're doing is we're taking the vector u, it has to go in the same direction, but basically the length of it or its magnitude, we're cutting it in half. So that's the best I could do drawing it by hand. So this is 1/2 times the vector u. Then in part B, we want to draw the vector 3u. So that means that we're essentially taking this vector and then we're putting along 3 of them. So the length or the magnitude of this vector u gets tripled. So let me try to draw this by hand. This is the direction, and then this would be vector 3u. And then the last one we have in part C, -2 times the vector u. So remember, if the A value is negative, then it has the opposite direction. So I'm going to have my vector u start here, and because it's going in the opposite direction, and then we're looking at the absolute value, that means the absolute value of A, which is 2, that means that it's getting doubled. So here's one length of u, and then I'm going to double it and say it looks something like that. So this would be -2 times vector u. And there are our answers for example 2. If we can add vectors together, we can certainly subtract vectors. So the difference of two vectors u and v is defined by vector u minus vector v is the same thing as vector u plus negative vector v, where negative vector v is the same thing as -1 times vector v. And this is the vector that has the same length as v, but the direction is the opposite of vector v. So example 3 says sketch the vector 2 times vector u minus vector v. And remember, if it helps you, we could rewrite this as 2 times vector u plus negative vector v, like that. So what I want to do is I want to take vector u, I want to double it. So I'm going to move over here. I'm going to double vector u and say it looks about there. So this is 2 times the vector u. And then for vector v, we're not going to change the length, but we're going to change the direction. So it goes in the opposite direction. Essentially, we're having it go 180 degrees the other way. And so I'm going to move this since we're going in the opposite direction. Okay, so vector v, again, I'm not changing its length, I'm only changing its direction. So now it's going here. So now my resulting vector, if I add these two vectors together, I'm going to start here and end here. So I'm going to go ahead and draw this. And then that is 2 times vector u minus vector v. So it's that pink one there. And that is our answer. I forgot to label, this is our vector -v here. All right, let's move on. Let's talk about vectors on the xy plane or the coordinate plane. To go from the initial point of the vector v as shown, the end point, we move a units to the right and b units up when a and b are both positive. So we can write that vector v is equal to, so notice that we're using these pointy brackets, so vector v is equal to a comma b, and then I have these pointy brackets here. We don't want to use parentheses because that might be mixed up as an ordered pair, so that's why we use these pointy brackets. And a is the horizontal component and b is the vertical component of v. So here's just a quick comment on the notation of vectors. Oftentimes when you see a vector in some kind of text material, like a textbook, the notation used for it will be a bolded variable that may look like vector v. And so notice here that this variable here is bolded. When handwriting, since it's difficult to bold our letters, we will use the notation v with an arrow above it. So that's just something to note. I will interchange or go through both notations when I'm typing documents, so you'll see both of those notations, so just know. So let's look at down below. Note that vector v has many different representations in the plane depending on its initial point. Therefore, two vectors are equal or the same if and only if their corresponding components are the same. So notice that I have two vector v's drawn here. So here's vector v and here is vector v. Those are actually the same vector even though they are in different locations because of the fact that vector v has a horizontal component of 4 units and a vertical component of 2 units. And same here, these have the same horizontal and vertical components. Therefore, these vectors are the same vector, regardless of the fact that they are located in different places on the xy plane. So here we have vector v graphed, vector v, or we could call it vector pq, because those are the 2 points that we're connecting with this vector. So let's talk about this formula. It's the component form of a vector. If a vector v is represented in the plane with initial point p, which is located at x1, y1, and terminal point q, which is located at x2, y2, then the vector v is equal to x2 minus x1, y2 minus y1, enclosed in these pointy brackets. So essentially what we're doing is, just like in this image that we had up here, we are looking for the components. So if this ordered pair right here is x1, y1, and this one is x2, y2, then to get the horizontal component, what we're doing is here, this point has an x coordinate of x2, this has x1, so then the horizontal component here is x2 minus x1. And then similarly here, if we're talking about the vertical component, we would get this by doing y2 minus y1. So that is where this formula here comes from, so that we can turn a vector into component form. Example 4 says, find the component form of the vector u with initial point 2, 4 and terminal point -1, 1, then sketch vector u. I think it might be actually easier if we start out with the sketch. So I'm going to plot the point 2, 4, which is right here, and then I will plot the point -1, 1, which is here, and make sure you are paying attention, because with vectors, remember, the terminal point and the initial point are not interchangeable because vectors have direction. So we need to make sure we're drawing our vector in the correct direction. All right, so I went ahead and I graphed vector u, so I'm going to label it now, and notice that the arrow is going in the southwest direction, because here this 2, 4 is our initial point, and then our terminal point was -1, 1. So that's why the arrow for our vector is going in the southwest direction. So now we want to find the component form. So vector u is equal to, I'm going to draw my pointy brackets. And if we go back to our formula, we see that it's the difference in the x-coordinates and then comma the difference in the y-coordinates. But be very careful. Remember, the order in which you subtract them matters because we have to think about the terminal point and the initial point. So let's go back down. So if I'm doing x2 minus x1, comma y2 minus y1, and I wanted to label these, I could label this one x2, this one y2, this one x1, and this one y1. So vector u in component form is equal to -1 minus 2, comma 1 minus 4. And if we simplify that, 1 minus 2 is -3. And then 1 minus 4 is also -3. So here is our final answer for our vector u in component form. Example 5 says if vector w is equal to 5, 3 and has initial point 1, -2, find its terminal point both algebraically as well as graphically. So let's go ahead and plot our initial point. 1, -2 would be right here. We'd go right 1 and then down 2 units. And our vector w is equal to 5, 3, which means that the horizontal component is 5. So that means we're going to move to the right direction, 5 units. So 1, 2, 3, 4, 5 would end us right here. And then our vertical component is 3, so I'd move up 1, 2, 3, which would end me there. I'm going to go ahead and erase this. That was just the placeholder to help me. And then I'm going to connect my initial point with my terminal point. So there is my line segment, and then I know that this was my initial point, so my terminal point is here, and that means that my vector is going kind of in the northeast direction. So right now we're asked to find the terminal point. Now be careful, the terminal point is not a vector, it's an ordered pair. So for this one, we're actually going to place it in parentheses. So the way that I get the terminal point is this is 1, 2, 3, 4, 5, 6, and then this is 1. So to get to our terminal point right here, the ordered pair is 6, 1. So there is our final answer. We did that graphically because I counted based off the graph. So how would this work if we were doing this algebraically? Well, I know that vector w is equal to x2 minus x1, comma y2 minus y1. And we are given the initial point, which is here, and it's 1, -2. And because this is the initial point, this would represent x1 and this would represent y1. And I also have the final component form of vector w. So this means that 5, 3 is equal to x2 minus 1, comma y2 minus -2. So if I were doing this algebraically, if I set the components equal to each other, so if I set x2 minus 1 equal to 5, that would give us x2 minus 1 equals 5, and so x2 would have to equal 6. And then if I set the vertical components equal to each other, I would say that y2 plus 2 is equal to 3. If I subtracted 2 on both sides, I get y2 is equal to 1. And so there also we get that our terminal point, I'm just going to abbreviate it to TP, is 6, 1. So that's another way we could have gotten our answer algebraically instead of graphically. So that completes example 5. So finally, we can start to talk about how we find the magnitude of a vector, which is essentially the vector's length. So the magnitude of a vector v is its length. If vector v is equal to a comma b, then the magnitude of this vector can be written as, these look like absolute value bars. And so, if we have a vector v, then its magnitude, we put these vertical bars around them, and it's given by this formula where we have the square root of a squared plus b squared. You can conveniently think of this as the hypotenuse of a right triangle, since the two components will represent the two distances, vertical and horizontal, to get from the initial point to the end point of the vector. So let's look at an example 6, which says, find the magnitudes of the vectors in the previous two examples. So let's remind ourselves. In example 4, we found that our vector u was equal to -3, -3. So if I want to find the magnitude of vector u, I'm going to use this formula. We have the square root of -3 quantity squared plus -3 quantity squared. So that's going to be the square root of 9 plus 9, which is equal to the square root of 18. It does not tell us whether to give this as an exact answer or a decimal approximation, so I'm going to simplify this. This is equivalent to 3 times the square root of 2, and then our decimal approximation, rounded to 2 decimal places, is 4.24. So these all represent the magnitude of vector u. And then in the previous example, the vector we were looking at, vector w, was equal to 5, 3. And if I want to find the magnitude of vector w, this is equal to the square root of 5 squared plus 3 squared. So let's see, 5 squared is 25, plus 3 squared is 9. So that would be the square root of 34. And again, if we rounded this to 2 decimal places, this would be equal to 5.83 approximately. So those are the magnitudes of the two vectors that we just looked at. Example 7 says find the magnitude of vector u, which has the components -4 and 3. So the magnitude of this vector is equal to the square root of -4 quantity squared plus 3 squared. So this is equal to 16 plus 9, which is 25, and the square root of 25 is 5. So this vector here has a length or magnitude of 5 units. So it turns out, again, in component form, we can add, subtract vectors, and we can also do something called scalar multiplication. So this thing here is called scalar multiplication, where we multiply a vector by, you guessed it, a scalar, where c is some real number. So using those properties, example 8 says, if vector u is equal to 1, -2, and vector v is equal to 0, 3, find the new vector 2 times vector v minus 3 times vector u. So let's go ahead and first compute 2 times vector v. That means that we're going to take our components and multiply them by 2. So 0 times 2 and 3 times 2. Actually, let me rearrange the order. Multiplication is commutative, so it ends up being the same, but I want to follow the formula that we have here, so it'd be 2 times 0, 2 times 3. So this is going to end up simplifying to 0, 6. Now let's go ahead and compute 3 times vector u. So I'm going to multiply 3 times the horizontal component and 3 times the vertical component. And if we do that, we get 3, -6. All right, so now we want to do 2 times vector v minus 3 times vector u. So this is going to equal 0, 6 minus the vector 3, -6. And if we're using this formula up here, I can combine that so it ends up being 0 minus 3 and 6 minus -6, which is probably pretty intuitive. That's probably what we would have guessed how subtracting vectors works in component form. And 0 minus 3 is -3, and 6 minus -6 ends up being +12. So here is our final answer. It is the vector -3, 12. The 0 vector is the vector, you could either write it with a bolded 0 or a 0 with an arrow over it, and it's just equal to 0, 0, and it plays the same role for the addition of vectors as the scalar 0 does for the addition of numbers. So let's look at some properties of vectors that will come in handy. You can look over these, and just the last one, the length of a vector, if you have some vector u and you multiply it by a scalar c, then the length of that new vector is, notice that this is not bolded, so we're taking the absolute value of our scalar c, and then we're taking the magnitude of our vector u and we're multiplying them together, and this should be, our final answer should just be a number or a scalar. Go ahead and look over the other properties and make sure that you are understanding each of those. So in this class, at the beginning of the course, we talked about something called a unit circle, which is a circle with radius 1. So now we're going to talk about unit vectors, and a vector of length 1 is called a unit vector. Example 9 wants us to determine if the given vectors are unit vectors. So in order to do that, in part A, I need to calculate the magnitude of this vector. So it's going to be equal to the square root of 3/5 quantity squared plus 4/5 quantity squared. So let's simplify this and see if it ends up equaling 1. So finally, we get that the magnitude of vector v here is equal to 1. Therefore, vector v is a unit vector. All right, let's look at part B now. So we want to take the magnitude of vector u. That's going to equal 0 squared plus 1 squared, and then we would take the square root of that. So that's going to equal the square root of 1, which is equal to 1. So therefore, vector u is also a unit vector. Now, in practice, most vectors, or more often than not, are not going to be unit vectors because usually they'll have lengths of something other than 1, but they become important when we think about other types of vectors. So two very useful vectors, or two very useful unit vectors, are defined as follows. So the I vector is equal to 1, 0, and the j vector is equal to 0, 1. Given what we know about component vectors, let's draw these two vectors below. So 1, 0, we're going to start at the origin, and we're going to move to the terminal point 1, 0, and then we would have this vector here, so that's vector I. And then vector j, we're still starting at the origin, and its terminal point is at 0, 1, so that would be right there, and this is vector j. So that's how we write vector I and vector j, these very special unit vectors. Example 10 says, on the grid provided above, graph the vector w, which is equal to 3, 2. Is there a way we can construct the vector w using the two vectors, vector I and vector j, using vector operations we have learned previously? Let's start out with the first part. So I want to graph 3, 2. So I'm going to go right 3 units from the origin and then up 2 units, and that would end me there. And my initial point would be at the origin. So let me go ahead and draw that vector. All right, so this is vector w that we just graphed, and it has the components 3, 2. And we want to know, can we construct this vector somehow using I and j? Well, let's think about it this way. If I took my I vector, let's say I scaled it by a factor of 3, my new I vector here, this would be 3i. And then what if I took j, and let's say I had j start here, but I had to double it to get to here. So now this would be the vector 2 times j. And notice that if I were to add these two blue vectors together, that would give me the vector w here. So let me draw it out here just so that we have it shown again. So here, this vector, I'm calling that 3i. And then here, this would be, maybe I'll make it a little bit longer because it's supposed to be double j. So this would be 2j. And if I added those together, my new vector would start here and it would end here. So this would be the vector 3i plus 2j, but that's exactly the vector that we had earlier with vector w. So to answer this second part of the question, is there a way that we can construct the vector w using I and j? We can say that vector w is equal to 3i plus 2j. So even though we did it in example 10, it turns out that any vector can be written or expressed in terms of I and j. So the vector u, let's say it has components a and b, can be expressed in terms of I and j by vector u is equal to a times I plus b times j. Example 11 says write vector v, which is equal to negative 4, 7 in terms of I and j, which is, the name for this is called standard basis form. So vector v is going to equal negative 4i plus 7j. So there is our final answer. Example 12 says if vector u is equal to 2j and vector v is equal to 3i plus 4j, write 2v minus 3u in terms of I and j. All right, so 2 times vector v minus 3 times vector u. So this is going to be 2 times the vector v, which we have 3, 4. Notice that I'm writing it in component form first, and then minus 3 times our vector u. So if it's 2j, that means that we essentially have that vector u is equal to 0i plus 2j. So then in component form, that would be 0, 2. So then I can start to multiply in. So 2 times our first vector would give us 6, 8, and then minus 0, 6, and then that would equal, let's see, 6 minus 0, and 8 minus 6, and so that will be 6, 2. But we still want to write it in terms of I and j, which again is called the standard basis form. So finally, this thing is equal to 6i plus 2j. So there is our final answer. Example 13 says, let's look at the vector u and vector v. For the new vectors requested, 1, we want to write the vector in component form, 2, write the vectors in terms of I and j, and 3, graph the vector on the grid provided below. So we want to look at the vector negative 1/2 times vector u. So let's write that in component form first. So this is going to be equal to negative 1/2 times 4, negative 2. And if I multiply each of the components by negative 1/2, that is going to give me negative 2, positive 1. All right, so here's the component form. Then in terms of I and j, so that would be negative 2 times vector I plus, we could put 1 times j, or we could just put vector j like that. Either is fine. And then we want to go ahead and graph that. So let's move on to part B, and then we'll do both graphs together. So here, vector u is 4, negative 2. And then I want to add this with 2 times the vector negative 1, 3. I'm going to start off by multiplying. So we get -2, 6. And now I'm going to go ahead and add those two vectors together. So that's going to be 2, 4. So here's one of our answers, and then we want to write it in terms of I and j, so that would be 2i plus 4j. So there is that. All right, so as a quick reminder, our original vector u was equal to 4, -2. So it doesn't ask us to graph vector u, but I'm just going to go ahead and graph it really quickly. So 4, -2 is down here. So that's vector u. And then we want to graph -1/2 times vector u, so that because it's negative, it would go in the opposite direction. And then because we're scaling it down by 1/2, we said earlier that this was equal to, let's see, -2, 1. So that would be right here. And so our new vector would look something like that. So this is -1/2 vector u. And let's go ahead and do the same thing for our other vector. All right, so our new vector for part B was 2i plus 4j. In other words, we want to go right 2 units and then up 4 units. So that would end us up here. And our initial point is still at the origin. So then our vector would look something like that. And this would be, you could either label it 2, 4 or 2i plus 4j. Either is fine. And there is our answer graphed for part B. All right, just so that we have a nicer graph, also on the right here, I went ahead and put in the computerized graphs so we can see the black vectors were the original given vectors, and then the blue or cyan vectors are the ones that we were asked to graph. So those are given for us here. And that completes this section.